Welcome to DeepMind, the podcast, where we're exploring the world of artificial intelligence. We're assessing what we know and what we don't know. We're looking at what we're trying to know. We're calculating what we will know, mapping out where we're going, and working out how we will know when we get there. I'm Hannah Fry, and I'm an associate professor in mathematics, and I've spent the last 12 months at DeepMind. And in this episode, we are going to start looking forwards to the future, the self-schooled variety of AI known as artificial general intelligence. But first, you know what? I don't feel like we've really given you the grand tour of this place. DeepMind headquarters in King's Cross in London. So follow me in my squeakiest of sneakers. Closed doors, coming through.
So the language group, they do machine learning, understanding language.
With me is the extremely likeable Koray Kovacoglou, one of the very first DeepMinders joining way back in 2012.
This area is a group of people who are really focused on agents, better memory, more planning. How can we get those into the agents?
All of your rooms are named after famous mathematicians. Einstein room, Gauss room, Hedy Lamarr.
Oh, actually, I know her. She's actually a very famous actress.
You know, I liked her best in I Take This Woman with Spencer Tracy.
But she was actually also a scientist, right? The deep learning group is more interested in just coming up with algorithms and architectures on any data domain.
Some seriously delicious equations on the whiteboard over there.
Yes, everywhere. I mean, blackboards and whiteboards.
If you have an idea in a corridor, it's important.
Yes.
Synthetic data to use.
So this area is the machine learning group. So one of the main projects going on here with this group is the imitation.
Oh, hang on. Here's someone we know.
Yeah, there you go.
That's just demonstrators in the office.
This is the area for the neuroscience group. They do a lot of thinking about what are the important problems, what are the challenges that we need to do.
Spin it really hard.
Ooh, table football. Yeah, table football's never been my forte. Rigorists. The reinforcement learning team.
This is one area that has been core to what we try to achieve with AGI. If we are interested in agents, it has to be active.
They've got some proper weighty textbooks. That's not exactly bedtime reading, is it? Molecular electronic structure theory. I know what all of those words mean, but just not in that particular order.
Sleeping pods.
Sleeping pods. I didn't know about these.
Well, energy pods, sorry.
About these. I've been coming here for a year. No one told me about these. Is there anyone in there?
Right.
Oh, sorry. Look, in my defence, she didn't have a do not disturb sign on the door. Okay, enough of that already. Back to the simple stuff, like solving the enigma of intelligence. Just one tiny snag before we get there. First, we're going to need a proper definition of what intelligence is. Because intelligence, you see, is quite a slippery beast to pin down. We've got a bit of a head start when it comes to human intelligence. Although it might not be everyone's favourite metric, IQ is one of the most stable psychological tests we have, and it does a pretty good job at measuring limited intelligence markers like reasoning and logic. But IQ still doesn't get us any closer to a definition of intelligence. If we're going to get anywhere with this, we need to define it properly. We need some way to capture what we mean by intelligence that works just as well for humans and dogs as rabbits and machines. And there have been a few suggestions for what intelligence is over the years. In 1921, the psychologist V. Henman said intelligence was the capacity for knowledge and knowledge possessed, which sounds quite good on the surface until you realise that it also applies to libraries. Libraries can possess knowledge. Do libraries count as intelligent? Probably not. In 1985, Marvin Minsky, the cognitive scientist, said that he thought intelligence was the ability to solve hard problems. And that seems a bit more like it. It also captures what AI has already proved it can do. Here's Raya Hadsell, Senior Research Scientist at DeepMind.
In the last few years, there's a huge number of different narrow specific things that programs can do as well as a human. They can interpret your voice as well as a human. They can maybe translate from English to French and back again almost as well as a human. They can recognize things in images almost as well as a human. These sort of narrow specific things.
That word narrow is not to downplay the transformative power of this sort of thing. Just in this series, we've looked at energy conservation, medical diagnosis and protein folding, all of which certainly show the machine's ability to solve hard problems, and all of which are examples of narrow AI. But real intelligence, general intelligence, that needs something else, something more. Some scientists have described intelligence as the capacity to learn or to profit by experience. Others think it's about adapting and thriving in the environment you find yourself in. But whoever you ask, most scientists agree that somewhere along the line, intelligence is something about your ability to interact with an external environment. And being able to adapt has to be part of it too, so you can't be fully familiar with the environment. You've got to be able to deal with unanticipated challenges that get thrown at you if you're intelligent. In 2007, after going through hundreds of competing arguments, Shane Legg, one of the 3 co-founders of DeepMind, wrote an influential paper in which he and his co-author tried to pin down precisely what was meant by intelligence. And here is the definition that they came up with. Intelligence measures an agent's ability to achieve goals in a wide range of environments. And that is what they are aiming for in this building. Here's a reminder of what senior research scientist Murray Shanahan told us in episode 4.
The holy grail of AI research is to build artificial general intelligence. So to build AI that is as good at doing an enormous variety of tasks as we humans are. So we are not specialists in that kind of way. You know, a young adult human can learn to do a huge number of things and can indeed do an enormous number of things and can adapt to a huge number of different challenges. You can learn to make food, you can learn to make a company, you can learn to build things, to fix things, you can do so many things, to have conversations, to rear children, so all of those things. And we really want to be able to build AI that has the same level of generality as that. And that's really still an open challenge. We don't really know quite how to get there.
But if anyone has an idea of what it will take, it's Demis Hassabis, the CEO and co-founder of DeepMind. We'll be talking to him in the next episode about AGI, but for now, here is a little glimpse into his thinking.
I'm waiting to see a lot of key moments. For example, I think a really big moment will be when an AI system comes up with a new scientific discovery that's of Nobel Prize winning level. That to me would be a big watershed moment. So, capable of some kind of true creativity in some sense. I think other big points will be when it can use language and converse with us in a naturalistic way. It's capable of learning abstract concepts. These are all things that I think are high level cognitive abilities that we're nowhere near yet, and I think will be big signposts on the way.
Now, it's reasonable to be asking yourself, how do you even approach such a colossal task? Where do you even start? Do you totally and completely believe that AGI is possible?
Yes.
That was a short answer, wasn't it? No, I knew.
Are you trying to trick me?
Back to my tour guide, Koray Kovachoğlu. He's the director of research at DeepMind.
I believe a day will come where we will be at that stage. Right now, we are not. Right now, all we can do is go back from that and then have a hypothesis about the important problems, the important algorithms that we need to develop, the important solutions, those key things we need to have, and then start building more and more and more.
So let's take an example then. Let's say the first day that someone at DeepMind decided they wanted to look at the problem of navigation. Right? So building an agent that you can drop into an environment
yes.
and it can work out where
yes.
it's going. Do you just have like a big brainstorm on a whiteboard of all of the different possible aspects that might contribute to being able to build that agent?
Yeah, it starts with that. Because if someone wants to work on something like that, then probably there will be a good number of people here who would be interested in the same thing. We would start discussing, okay, what is the goal? Like when we say navigation, you gave a particularly good example, right? Like going from here to a given location. How are we going to specify it? What kind of environment this is? What kind of control space does the agent have? All these start affecting what kind of algorithms we should use. And are we going to do this purely from vision? Are we going to do this in a simple environment, in a grid world? Or we're going to start from a grid world and then we need to think about a path towards going to a 3D environment? Are we thinking about actually also putting this on a robot, like with real vision? Like all that discussion starts happening.
It's massive then. I mean, just
Yes.
that one problem is enormous.
It is, but that's why it's also research. A big part of it is trying to constrain the problem space, like being able to write down and specify what you want to do, and then making sure that it is actually a challenging problem, and there are good metrics that we can quantify our
A way
solution.
to say you're successful.
Right, exactly. And that itself, as I said, is quite an iterative process. And getting that critique, getting that view from other researchers starts at that point in time. Because like when the research is at the idea space, at the initial stages, it's actually quite important to formulate the right problems and sort of the right context.
AGI is not going to happen overnight. It's the reason why, as you heard on the tour, there are so many different research groups in this building. You're not going to crack AGI by attacking on only one front. And formulating the right problems means going beyond individual skills like navigation and drilling down into the building blocks of intelligence and tackling those too.
From the beginning of DeepMind, if the goal is about AGI, then it has to involve control. It has to involve an active algorithm. And that is why you need to do reinforcement learning. That is why you need to work on agents.
We need agents that can interact with their environment, that can learn through trial and error what actions to take, what Karai calls its policy. It's a fundamental thing that you would expect to find in any intelligent being, humans, dogs, or agents. And so if the scientists can get it right in one application, the lessons learned should apply elsewhere.
The gist of training an agent is you can start completely from scratch. And then slowly the agent builds that knowledge, that strategy of how to achieve a certain task. And it creates, it builds, it comes up with its own strategies. It comes up with its own policy. So then, of course, looking at it and trying to understand, does that policy make sense? Why is it doing that policy? Sometimes it's so surprising because it's something that we haven't thought about before. Sometimes you look at it and you see that, that doesn't make sense. Yes, it achieves something, but it's clearly not optimal.
Can you remember when you first realised or believed that AGI was possible?
So we tried these agents on Atari games and they didn't do much. And we couldn't make them work, right? Like there was a team of like several people there and we couldn't make them work. And then slowly we started simplifying the problem and simplifying the problem and simplifying the problem. And we ended up with a very tiny, simple, trivial problem. Really just like a 5 pixel by 10 pixel image and 1 pixel moving in that image and the agent trying to control that. And once we reduced the problem to that, which I call the MNIST of reinforcement learning, really, we could find a working solution. We started having these deep reinforcement learning agents working, right? Because it's a simple problem. Of course, you can write a program to solve that, but the idea was like, try to do deep reinforcement learning and try to solve it that way. Try to solve it from pixels. Try to come up with a system that we think can generalize to different problems, to more problems. And once we solved that, actually it was a matter of weeks. We had 10 or 15 Atari games like being solved. Like from that tiny thing, in the matter of weeks, you go to Atari. That was a big moment. That's what we keep on going. That like we select more and more diverse set of problems that we think are important at the end for AGI.
That is a key point. Here, intelligence is an agent's ability to achieve goals in a wide range of environments. So to get to AGI, we need agents to solve harder and more diverse problems. You're listening to DeepMind, the podcast, a window on AI research. The closer we get to AGI, the more powerful and sophisticated this technology gets. And the more we rely on it in our everyday lives, the more dramatic the consequences could be of us misunderstanding the limitations of the algorithms. And that is why, in parallel to pushing the science forward, researchers are also working to ensure, right now, that agents are reliable, adaptable, and crucially, not corruptible.
You show the image of a bus to a neural network, and it will say this is a bus, right? There's a bus in this image. Well, it turns out that you can take the same image, modify it a little bit, which is almost invisible to a human eye, but the neural network will say that it's actually an ostrich. These adversarial attacks are things most of the time that are invisible to the human eye, that doesn't change the actual content of the image too much. We don't perceive it. But because these are algorithms and they are sensitive to even very small fluctuations in the input data, then it changes the output.
Why does that matter? Why do you want to stop that from happening in sort of real-world AI?
Well, for two reasons. One of them, as I said, is robustness. Because when we train these algorithms, we want them to be useful in real world. And we train them on data sets that we captured from real world, but like you cannot know exactly what's going to happen, of course, what kind of data is going to be at the end of the day this algorithm is going to consume. So we want to make sure that the algorithms are robust to these kinds of potential like noise-like things, that you want your algorithm to be robust to that, right? And from another point of view, it's about safety. Being able to say that like someone maybe with an adversarial intent won't be able to change the output of this algorithm, output of this neural network, just by making very small adjustments to the inputs. We have a whole research group actually on that, on working on rigorous and more robust artificial intelligence, because yes, these are real things. In the end, we are training these algorithms, and as I said, it's not just like looking at them, but we're trying to do more quantifiable research on understanding why they are doing what they are doing and trying to interpret that. And part of it is also understanding how robust they are.
We have already seen real examples of just how fragile intelligence can be. Researchers have shown that you can add a little bit of black tape to a stop sign that will trick a driverless car into speeding up. The tape is so subtle that it would look innocuous to a human driver, but it's just enough to make the algorithms inside the car misread it as a 45-mile-an-hour speed limit sign instead of an instruction to stop. Other scientists have worked out how to fool facial recognition algorithms into thinking someone is Mia Jokovic just by making them wear a specially designed pair of tortoiseshell glasses. And the images that are used for medical diagnoses can end up giving wildly inaccurate results, just if a slightly different brand of scanner was used to take them.
You want to reach a state where you can actually guarantee that things like that won't happen. That's the main idea behind doing this research. So not sort of try to defend against particular adversarial attacks or examples, but actually come up with systems that are going to be robust no matter what. From the other point of view, of course, if you're thinking about agents, there's the whole safety issue.
What do you mean? When you guys talk about safety, what are you actually talking about?
if we have an intelligent algorithm making decisions for itself, you want to have some sort of guarantees that when it's acting with its own policy, it is aligned with what you intended it to do. If you think that these algorithms continue learning all the time, then we want that process to be also producing an agent that is aligned with what we have intended for it to do.
Fill in the gaps for me a little bit. Give an example of what you're trying to avoid.
It becomes quite technical in the sense that it's not like you are trying to avoid the agent from making a mistake, right? Because mistakes happen, right? Like we train policies and they are not always optimal. They don't do the right thing all the time. It's not about that really. It's more about you have a learning algorithm and you want to make sure that it sort of conforms to certain boundaries of behavior in a sense.
If we can develop safe, robust, ethical AGI, then the impact could be staggering. But as Demis mentioned, so too could the discoveries on the way to AGI, as agents learn to solve increasingly hard problems. Trevor Back is a product manager for the DeepMind Science Programme. He played a key role in the Moorfields Eye Hospital collaboration that we talked about in episode 5. But he also has a hand in deciding what the future holds for DeepMind and what challenges and opportunities lay in store for them to tackle next.
So we're really at the stage of exploring what other areas we should work on, but the possibilities are endless. If you look at the way the AlphaFold system works, there's nothing really specific in there to protein folding. It's around understanding the way that atoms interact, the way that you can build material from base concepts. So looking at material design is a really exciting stage. Could you design or imagine a high temperature superconductor that's been sort of brought to life through an AI algorithm, right? Is there more efficient ways of looking for those types of materials?
Why do we care about high temperature superconductors?
So this is the amazing opportunity of working in science. So our previous work in healthcare has been focused on very specific problems, and it takes a lot of time and effort and energy to build an AI system that works for those specific problems. If instead you can spend your time and energy solving a fundamental science question, then perhaps you can, instigate a whole new field of interest and potentially impact a much wider array of problems. So why is superconductivity a problem? If you could solve superconductivity, not only could you, solve a lot of the energy problems by having a larger magnetic field around fusion, but you could also create a new type of computing system. There's lots of opportunities that come from just a single breakthrough in one of these areas.
I think it's important not to understate this, because the idea that you could have some kind of an impact on nuclear fusion, for example, the implications for the Earth and humanity are just enormous, right?
Exactly. I think this is the reason I came to DeepMind, was the opportunity to have the greatest impact I could in the world. And I think AI is one of those revolutionary technologies that amazingly could, impact everything we do, but also everything we think about doing in the future. And the sort of opportunity to explore and search the space of opportunities is really something that's well designed for AI to do. It's a very efficient search algorithm. And so if you're able to set up the problem in such a way that is searchable via AI, you really could have 10, 100-fold type of increase in the opportunity for finding novel materials or finding anomalies in astronomical data, finding new types of stars, finding more black holes. All these types of opportunities are available simply via the application of AI.
And it's not stupid to say that actually lots of the biggest problems that face humanity at the moment are science problems, right? Like, access to food and water, climate change, healthcare, all of these things is stuff that AI can make progress in.
I think that's right. I think a lot of the sort of physical problems that exist in the real world are certainly things that if you can make a difference to some of the sort of foundational science aspects, you could reduce the cost of energy essentially down to zero, or you could make food more readily available across the world. And so that would really help society progress in a number of ways.
It's a tantalising prospect. Solving intelligence and creating AGI will take the full range of research explored in this podcast and more. Memory, reasoning, logic, learning, language, embodied cognition, and more. So much more. And we're going to explore some of those ideas in our next episode, when I meet with DeepMind co-founder Demis Hassabis. He tells us how he created the world's leading AI research outfit, reveals what keeps him up at night, and opens up about his hopes for the future.
I'm just fascinated and also troubled by the things around us that we seemingly don't understand. All the big questions, the meaning of life, how did the universe start, what is consciousness, all these questions, which I feel like a blaring sort of klaxon in my mind that I would like to understand. And my attempt at doing that is to build AI first.
If you would like to find out more about artificial general intelligence or explore the world of AI research beyond DeepMind, you'll find plenty of useful links in the show notes for each episode. And if there are stories or resources that you think other listeners would find helpful, then let us know. You can message us on Twitter or email the team at podcast@deepmind.com. You can also use that address to send us your questions or feedback on the series.